So we are on hypothesis testing. So hypothesis testing, and let me see if I can move this out of the way and only show the tabs. Yeah. Hypothesis testing is kind of the other side of confidence intervals. So remember, we looked at confidence intervals and you had your nice little normal distribution and we set up those goalposts and we were like, all right, like I don't want to just be picking one thing or groups of things. If I was going to do this a bunch of times, would it land in this reasonable zone right here, right? In those goalposts where we can say, yeah, that this is where I can be like X% confident that the true population parameter lives, right? So we were hoping to kind of find things that fall inside the normal stuff, like the usual values. What hypothesis testing does is the other side of that. So now, often, not always, you're looking to fall outside of that normal zone because you want to have been doing something that shakes things up. It makes things better, makes it, probably not make it worse, but like maybe making it better is increasing it, maybe making it better is reducing it. And so you can see, like, did I make it better or did nothing happen? And you can test that directly too, where you tend to kind of fall inside that same confidence interval. You don't see a lot of confidence interval things in studies where the confidence interval is the star of the show. Like a lot of times the confidence intervals are reported, but because you can then from that pull out the hypothesis test. So we're going to look at two hypothesis tests today, one next week. The good news is most confidence intervals, they all kind of have the same spiel. Like you're going to do the same thing for each one. Now, why textbooks do stuff like this, where they list everything out separately, I'll never understand, because knowing how to do one single part or studying one single part alone is not really helpful. Like you need to know the whole list. So what we're going to kind of do is just kind of smush all of this into like, this is how you do a hypothesis test for population proportion. This is how you do a hypothesis test for a mean. And that process is going to look pretty much the same. You're just talking about different things, right? So this was just kind of the spiel I talked about, where confidence intervals, we wanted to know what was happening on the normal times and what we can expect, where the hypothesis test is like, what changes did we make? So now a hypothesis is very similar to when you were in like your science classes, right? You're going to make a claim, a statement, something about your overall population. Like this is what I think is happening. We're actually going to have two. And then we're going to go about testing that hypothesis. And we are usually actually not testing the claim itself. We're usually testing the status quo and seeing if it falls in or if it falls out. So we're going to actually have two hypothesis statements then, because if my claim is like something's better or something's worse, but I'm testing the status quo, then I need to have both of those two hypotheses. So I'm going to have two hypothesis statements. They're going to be disjoint. So those are going to be ones where either I land in the middle here or I'm on the outside. Maybe outside just one side, maybe outside just the other side, maybe I don't care what side. But those two things, when you hook it all up together, is going to be the full confidence, the full normal distribution. Right, so then you're going to collect sample data. And these kinds of problems, we're going to have sample data, and you'll know what your hypothesis and your claims are going to be. And then you're going to perform the hypothesis test, which we're going to have calculators. Some are better than others. And then you're going to make a decision, and you're going to write a statement. The statement is what gets everybody. There's lots of different ways that you can do the statements. Going to actually I already did. I sent it to you last night, and I have it in the slides, even though it looks a tiny bit different. The hypothesis flow chart, right? So you want to follow that to get down to what I call the magic sentence. Are there other correct ways to write it? Yes, but on the final exam, that's what they use, right? They use those magic sentences. So if you just follow the flow chart, you'll be in good shape. Our two hypothesis statements are called the null and the alternative. So the null is the status quo. That is the thing that we know is true, has been put forth as being the truth, and that is actually the thing that we're going to test directly, right? So we test the null, like, do you hold up to the thing that we know to be true? The alternate is, oh, and that's to say H sub 1 or H sub A. I use H sub 1 because my handwriting is bad, but you can use H sub A for alternate, and it is the other part of the null hypothesis that picks up the rest of it, the rest of whatever is going on with your claim. So usually you write the alternate first, and then you back up into the null. After you do that, you run your test, and you're going to get something called a test stat and a p-value, and you're going to make a decision holding these two hypotheses testing, which one am I going to keep or which one am I going to get rid of? Now, your null is always going to have the equal sign. Let me get this up right here. And we're going to go through this a little bit more deeply. We usually just write the equal. You can write it with the greater than or less than or equal, but they usually don't do that. They usually just say that. Where your alternate is always, or I should say, I was going to say always never, right? Is never going to have the equal sign. So equals always over here, and all the other stuff goes over here. The less than, the greater than, or the not equal. But this one is always the equal sign, right? So then we have these other parts of our process here. So we write these two hypothesis statements, we calculate this, and we kind of figure out what's going on with the chart. Calculate this, and then make a decision. So it's like 1, 2, 3, 4, 5-ish steps. The hypothesis statements are going to be super important because we're not crunching this by hand. So we're going to put this in a calculator, and it relies on the hypothesis statements to kind of crunch those numbers properly for you. So let me make this bigger. I want this to be bigger, but it doesn't want to be bigger. That's H sub 0, H sub not. You can just call it the null. We always test the null directly. That is what you kind of want to take away from it. So when you're done with your test and you write your magic sentence, it may be a little unfulfilling because we're talking about keeping the null or reject the null or fail to reject the null. So even if you were like right, you won't hear something that says like you were right. This is always with the equal statement. The alternate could be the claim, but it's probably not, and it's going to use the not equal to, the less than, or the greater than. So what does this look like? Let's say I have the storyline. Let's see. Where's the rest of the story? Let's go to this. We want to test if students take less than 5 years to graduate from college on average. So if I want to test, if my claim is that they take less than 5 years, then that's less than 5. That's my claim. And so I jot that down and I think, well, what's the opposite of less than? Greater than or equal to. And as soon as I say the equal to, I know that that's my null. So my null statement is whatever parameter I'm talking about. In this case, it's a mu that is greater than or equal to the 5, which I would probably just write the equal. And then my alternate, so my H sub A, my H sub 1 is mu is less than the 5. And I usually star my claim just so I can kind of keep track. And so that is those my two hypothesis statements. We're actually going to start with population proportion. So News and World Report article on standards stated about half of all students in France, Germany, Israel take advanced placement exams and a third pass. So in the United States, only about 6.6 students take advanced placement test. Test the percentage of U.S. students who take the advanced placement exam is more than 6.6 6%. So my claim is, no, 6.6 is much too low. My claim is that percent is greater than 6.6%. It's the opposite of greater than, less than or equal to. And if I say equal to, that's my null. So I would probably just put just an equal sign just in like that, and then star this so that I remember that it's my claim. After you do that, and we're going to do a few of these things by hand just so you can kind of see what's going on, you would then take your sample data and calculate what's called a test statistic. Now, just like with the confidence intervals, all of those error rate, all those margin of errors had a different formula. Same thing with the test stat. I'll show you how to calculate it by hand. These are our lovely formulas over here to the right. Well, you don't really need to do it by hand because the calculator, whether you use the TI or any of the websites, they're always going to give you the test stat and do all of that for you. So you get this test stat, and then what you're going to do is figure out where it lands in the world of what you're studying. And the map of the world of what you're studying is going to be the normal distribution. And you're going to carve it up depending on what significant level they tell you that they want you to have. This is the other side of that confidence level, right? So if you were 95% confident, remember it was 95 in and 5% out, the 5% out is the tails. I'm going to put all of it on one side, like just left or just right, or am I going to have some on each side? So since 90, 95, and 99 were the popular confidence intervals, right? That means that our significance levels is usually a 0.05, 0.01, or a 0.10. 0.05 by far the most popular. All of that outside is going to be the critical region. It could be just one tail, or it could be some on each side and be two tails. And those rejection regions are walled off by that critical value, right? So the critical value that set up the goalpost for your confidence intervals, now instead of like keeping stuff in, it's keeping stuff out. So what I would do is I would have something, let's say I have a two-tail test, so because that's the most like my confidence interval. And let's say I want my alpha to be a 0.05. Remember that was 95 in, 5% out, half on each side. And so I would say 0.025, 0.025, and this is my rejection zone. So if I think about my test stat as a dart and I throw my dart at this map, if it lands in the rejection zone, that means I'm going to reject the null. If it lands inside the big zone, the confidence interval area, then I'm going to keep the null. And these little spots of where you know to put up the wall is called the critical value. Those are the trickiest, I think, to get your hands on. Most calculators will give them to you, but not all of them, and the TI doesn't, which is why most people use what's called a p-value to figure out what you're going to do. So remember, you might remember me saying, like, there's a lot of p's in this course, right? We got p for probability, we got p hat, we got p for population proportion. Now we got p-value. P-value by far is like, if somebody says p in stats, this is probably what they mean. A p-value is the area underneath the curve from the test stat to wherever the infinity is that it matches. So if I have a one-tailed test, let's say I have a left-tailed test and I'm looking at something right here. And then I throw my dart at the map and it lands right here, right in this spot. The p-value is the area under the curve from here to the infinity that it matches most of the time. Just head towards the tail. Now, if you have two rejection zones, you're going to only get one test stat, and you're going to have to put it over that full line at that x bar equals 0 and then multiply it by 2. But the calcs do this for you. So you're probably not going to be like busting out charts and calculators and finding inverse norm, right? Like you're going to put it all in, and if you tell it properly, hey, this was this kind of symbol in my alternate, it knows how to calculate the p-values for you. that's why we use p-values a lot instead of the critical values. But whether or not you say, hey, did you land to the left or the right of the cutoff value, or you talk about how much of a area it scoops up, either way, you're going to get the same decision to reject the null or fail to reject the null. So how do you know if you reject the null or fail to reject the null? Well, if you land in, let me go back to this one, the critical regions over here, then you reject the null. So that is going to be if your p-value is less than whatever this value is here, or if your test stat lands too far in this region, right? So if you throw a dart at the map and it lands here, and you know what this score is for the cutoff, then you know you land in that region. If you don't know that and you're just going to go by p-value, it's find the area under the curve to the end here, and then you would say, oh, I did not spill over into the middle here. You see how I have that extra space? So I'm still in the rejection region. So I'm rejecting the null. You reject the low when the p is low. If the p-value you have is less than your significance level, you reject the null. The p is low, the null goes. That's the magic sentence. Like that's how you figure out what you're going to do. If the p is low, the null goes. If the p is lower than the significance value, you reject the null. If it's bigger, you fail to reject the null. If you throw a dart at the map and you land in the big zone, you keep the null. If you land in the little zone, you reject the null. So that's, think to yourself, if the p is low, the null goes. So if you know where you land and you can compare it, that's the critical value method. Or you can use the p-value, which is what most people do. And then it's the worst part. You got the flow chart. And you have to say, did my original claim contain the equality? Right? Was my claim that this thing is equal to? Because it could be. Then, like, let's say I want to say that the test scores are equal to 50. Then yes, my original claim wasn't equal, so I would go this way. Most of the time, it's that it's less than or greater than or something like that. So then you come down this way. And then you have to say, did you reject the null? Yes or no. And then you are going to land in one of these magic statements here. Now, it will say something like the sample data supports a claim that, and then you would put in whatever the original claim is, but you really don't, you can stop at the sample data supports the claim. That's totally fine. So it's a little bit, it sounds like a very long process. It's a relatively long process by hand, but with the calculators, it's not too bad. But you got to make sure that you're telling the calculator the right hypothesis statements, because that is what's going to say, are you a two-tailed, a left tail, or a right tail? And if you go the wrong direction, the p-values get all screwed up. Or if you only say it's a left tail and it's a two-tail, then you're missing half of your p-values. So this is the most important thing. You have a two-tailed test if you're claiming that something is equal to or something is not equal to. So if you're null, which of course always has the equal sign, that's your claim. Or your claim is that it's not, that it's different than, that it's not equal to, and so that it's in the H sub 1 with the not equal to. This combination right here is the only combination that is going to get you a two-tailed test, half on each side. So like if your sigma was a 0.10, you would say, oh, well, I got to crack that in half because I have this two-tailed test, so that'd be 0.05 this way and 0.05 this way. If you have a less than or greater than in your H sub 1 or your H sub A, then you're going to follow the point. So if I'm saying, oh no, I think that all of this stuff is less than that number, I'm going to take all of my alpha and dump it all over in there. And notice that that points left, so everything goes left. If you're saying, oh no, I think everything's greater than, then I have a right tail test, so everything's going to dump on the top. So you follow the arrow. No arrow, then it's both. That's it. You notice for each one of these, The null's got the equal sign. The null always has the equal sign. Right, so there's that summary for left tail, right tail, two tail. That's going to be a big deal because it sets up the map, and it's going to be able, that's what's going to calculate your p-values and your critical values. The test stat you can screw up like your tails, and you're going to get the same test stat. So this is the, I would say, unhelpful procedure list, right? Like this is what you would do if you're doing this test. And then you have this choice in here to use a p-value method or a critical value method. You're going to get the same kind of information. You're going to get the same result either way. And you are usually able to choose depending on the type of calculator that you use. We call the traditional method the critical value method, and the p-value method is the p-value method. So if you're reading something and you're like, what the heck is a traditional method? That means they want critical values. Most of the time they don't say anything, and I tried to say, give me whatever you want. Either give me a critical value or give me a p-value, because it doesn't matter what you use. P-values come from, just to kind of drive this home, because I know there's a lot of terminology, comes from the test stat shooting off to the infinity that it matches. So if your test stat is like a negative 1.5, then it's from negative infinity to negative 1.5. If your test stat is 2.3, then it's 2.3 up to positive infinity. Those are going to, could they not match? They could not match, but it's pretty unlikely. Now, even if you have a two-tail test, you're only going to get one test stat. So just do whatever, go up to whatever infinity it is. And then if you're doing it by hand, you would say times 2. But the calculator will do that for you. All right. So let's kind of look at an example. This one is for population proportion, and then we're going to do a few of those, and then we're going to do a couple of meat. Majority of consumers are not comfortable with drone deliveries. 1,009 consumers were asked, hey, are you comfortable with drone deliveries? And 54%, which would be 545 of them, responded no. So remember in confidence intervals that p hat, where can I write it? P hat is x divided by n. Same thing here. Sometimes you want to use the percent, which would be this, right? Sometimes you want to use the x, which would be that. Depends to you. Using P to denote the proportion of consumers not comfortable with drone delivery. So this is basically just identifying this is a success. Like we're happy if they say, no, we don't like this. I guess so we don't have to go out and buy drones. That the majority, so we'll assume a simple majority of more than 50% is not comfortable with drone delivery. So my claim is that more than half, the majority of people are uncomfortable with claim drone delivery. So more, right, greater than 50%. That's my claim. So I got my claim, greater than 50%. And then I want to find, well, if you're not in that 50%, what's all the other stuff? Well, if I'm not greater than, I'm less than or equal to. And of course, that is going to be my null. And so I have my two statements. So I have my greater than, and then they wrote it like this. I would probably just write it like this. Oops, like that. So I have my null. P is equal to 0.5. And I have my alternate, which is P is less, greater than 0.5, and that's my claim, and I star my claim, because you want to think about, I'm holding both of these things. And the thing that has the star in it, you're really hoping to keep, right? Because one's got to go in the garbage. And so you want to be the one that says, yeah, you were right, what your claim was. So now what I need to do, let's see if we can go, is figure out what my map looks like and get my test stat. Do we have a test stat? Yeah, no. So the significance level is going to be given in the question. I would say probably this one would be probably a 0.05. And then I would find my test stat. Now, if I was doing this by hand, I would use this lovely little item right over here and calculate where my dart is going to land on the map. And so that would be at a 2.54. So it would have something on the map that looks like this. I have a right tail test, so all my errors in here, let's say it's 0.05. I threw my dart at the map and it lands at 2.55 when I round, but I don't know what side that's on. I don't know what side that's on. And let's say I don't know how to find that. I don't know what to do. I don't know how to find that cutoff. Well, then I can use the p-value because I know how to find the area of this up to positive infinity. I could use statlet if I wanted to. Let me find statlet. I'm in z-score world for this. So it's a normal distribution. And area to the right of 2.55. And that's 0.0. So this is a little deceiving, right? Because this is actually 0.0054 as a decimal. So this is actually much smaller than 0.5 because that would be 50, or 0.05 because that would be 5%. So that means I land over here in this region. So I'm going to reject the null. And if your p-value, if that is less than your significance value, which this definitely is, then I'm going to reject the null. P is low, no go. So I reject the null. Oh, good, I do have it now. It looks like that. So then I would follow my chart down, which I don't have in this section, so I'm going to come back to this for a second so I can find that chart for you. Did my literal claim contain the equality? No, I said that it was more than, so I came this way. Did I reject the null? Yes. The sample data supports the claim that the majority of people don't want stuff delivered to them by drone. They're not comfortable with that. So you get used to it. It's not terrible to do by hand, but it's a whole lot easier with a calculator. I like the Stat calculator for this one, for the one sample proportion test. You're going to have some extra goodies on there that you don't need to worry about. Let me see, like don't worry about continuity. Don't worry about effect size. What you're going to do is you're going to match the symbol that's in your alternate to right here. Remember, my alternate was that P was greater than 0.5. Don't worry about all the symbols, you know, like P, P naught, H sub 1, right? Match this to that, and you'll be fine every time. Same thing on the calculator. Digits, you want to up it to 8, 10, whatever, that's fine. 6 will probably be fine. Significance level is whatever they tell you. If they don't tell you, they like forget to tell you, like me, forget to tell you, it's probably 0.05. You can name it or not name it. You know how that goes with Stats Kingdom. Now this expected proportion, this is the number that is in the hypothesis statements. So when you go back to your hypothesis statements, that's that number that comes in here for the expected. And then over here, you're going to say how many things gave you what you want, or the percent of things that it was. I think it was, I forget what the percentage was, but I remember it was 545. And then your sample size. And then you're going to hit calculate z-test. Calculate z-test. Then you're going to get some stuff. And so you kind of want to look for the red stuff. Here's my test stat. Here's my p-value. You could use either one of those, but p-value, you want to compare that to the alpha. So that's a little bit easier. For the test stat, you have to look inside of here and look for those cutoff values to see where it lands. It is not great at wording it in a way that will make sense. So what I would do if I were you is I would just grab the p-value and say, all right, here's my p-value. Here's my significance value. Is the p-value lower than the significance value? And then go from there. And you'll get the same answer as if you did it by hand or if you did the critical value and you wanted to like look up the critical values at Staplett. I know it's confusing. There's p-value, there's p-hat. At this point, if you see something that says p in a question, it's probably proportion. If you see something at the end of the question, then it's probably probability for p-value. You're probably not going to see a whole ton of like this one or this one anymore. Most of the time at this point, if you see something that's labeled p, it's probably a p-value. Okay. I lost where you guys are. There we are. I'm about to jump into some more proportion examples, questions so far. All right. Know that, jump in at any time. You got a question, just put it right in the chat. We'll figure it out. Oh, I got a question. I'm going to give you this because I'm going to guess you kind of want that. Yep, I'm going to go over more examples than you probably want. This is the proportion, one sample proportion test, hypothesis test for population proportion calculator. I would say I think I like this one the best. There is another one. Let me see if I can find it. That's mean. This is the other one. I put both of these in the thing the other day. I kind of like the first one. Maybe because I can remember the website easier than this one. Every time I have to like pull up my own email to find this. All right, here we go. And a sample size. There's that p, that is a population proportion. P-value is area under the curve. We're not going to do a lot of these by hand. Technically, right, there should be requirements. I'm not going to ask you to verify any of these. They are the same types of things that you have for your binomial distributions, the same thing that you have for your confidence intervals. Right? It's got to be a simple random sample binomial distribution. And you have to have a certain number of successes and failures, right? Because it's just it's the outside of the confidence interval, right? It's the lawn and backyard of a confidence interval. That's the test stat that you would calculate if you were doing this by hand, but you're not going to do it by hand. That's totally fine. If you want to know number of successes instead of using a percent, because you feel like maybe that would be more accurate, or vice versa. So it's either p-hat, probability of success, is x divided by n. And if you want x, then you just say n times the p-hat, where as a decimal. Oh, I feel like I went past that really quickly. There we go. All right. I don't think I have any real numbers in this round of PowerPoint for you. Sleepwalking. A study of sleepwalking or nocturnal wandering was described in the Neurology magazine. I can't get that word out. It included information that 29.2% of the 19,136 American adults that were surveyed sleepwalk. What's the actual number of adults who have sleepwalked, right? Because this is just the sample. So we know our best point estimate is going to be whatever we found, which is 29.2% of the 19,136. So that is 5587 and some change. Now, you can't have half a person. So you're going to want to put in 5588. I would just round mathematically for these. And what we want to do is we want to say, is it fair for us to say, if we want to name this journal article, fewer than 30% of adults sleepwalk? Is that accurate? So we're going to use a 0.05 significance level to test the claim that the proportion of those who have sleepwalked is less than 30%. That's my claim. So I say, oh, the proportion of people who sleepwalk is less than 30%, which is p less than 0.3. So then I have to think, well, what's the opposite of that after I allegedly check these things? That the opposite of, There we go. Is the opposite of less than is greater than or equal to. And if I say equal to, I have the null. So these are my two hypothesis statements. The one with the equal sign always gets the not. Equal to and not equal to are two different things. H sub 0 will always be some letter equal to some number. Always and forever. The alternate is going to be some letter less than, greater than, or not equal to the same number in both. So this is my claim. So I'm going to start so I can remember what I throw away if I'm happy or not. So now I need to think about what my test stat is and what my map looks like. So we're going to use a 0.05 significance level. And my alternate had a little arrow, right? So all my error is over here. And so my 0.05 goes here. And my 0.95 goes here. Now, population proportion stuff is in Z-score world. So I could find out where this is, or I could not. Either way is fine. But what I need to do now is take the stuff that I found in my sample and calculate my test stat. If I throw my test stat dart at the map, where is it going to land? Over here in the rejection zone, or in this big zone, which is the fail to reject? So I can calculate that by hand, but we won't. I'll show you the calculator in a minute. And I said, oh, I land at negative 2.41, blah, blah, blah. Well, where the heck does that land on my chart? So if I come here, I'm not really sure where it lands. So this negative 2.4 will land in there or in here. So I need to find out what my p-value is. The p-value to the left, since it's a negative 2.41, to the infinity that matches, so it's down, is 0.0008, very small. 0.0008. Is 0.0008 less than 0.05? Yes. So that means I land over here in this zone. So I reject the null. So I would say reject the null. And then I go to my chart and I work my way down. I don't know why I have the chart in more places in the next bunch of slides. Here we go. Did my original claim contain the equality? No. I said it was less than. Did I reject the null? Yes. Sample data supports the claim. So my sample data supports the claim that it'd be fair to say fewer than 30% of people have slept walk. I'm not even really entirely sure that the right way to say that. I'm going to go back to that slide like that. Thought I heard something pop up. Oh, yeah. So if it says 0.8, how many zeros? If it says 0.8%, then to change that to a decimal, you have to go back 2 decimal places. So that's why it's 0.008 as a decimal. So 0.8% is 0.008 as a decimal, which is why you're probably not going to do this by hand. You're going to go to your calculator and say, oh, my claim, let me make this a little bit bigger so you can see what's going on here, is a less than. So I'm going to say less than right there. I leave that alone. I put in my 0.05. I leave that alone. I leave that alone. I can name it, not name it, don't matter. My number that is in my hypothesis statements goes in there. Now this is either the percentage or the total number. So I think we found like 5588, but we had to round. So I'm going to leave it as 0.292, but you need to put it, you don't want percents. You want stuff going in as decimals. So 29.2% as a decimal is 0.292. And then I put in my sample size. and I hit calculate test. And then you get a bunch of stuff. Go for the red. Here's your p-value. This is your test stat. This is what's setting up your critical value. So remember when I said, oh, I don't know where it lands, right? I know this, but I don't know what this is. Well, that's a negative 1.645. So then I know I definitely land in here at a negative 2.41. It doesn't tell you the magic sentence that you have to do on your own. Let me pull up the calculator for a second with all of my calculators here. All right, so let's see. This is a one sample t-test. No, we don't want, we want proportion, okay? So when you go to this, the default is going to be on a not equal to. Honestly, you don't see that one a whole lot unless I purposely write one so that you have to do one that's a two sample test. I'm going to match this. So I said less than, right? So this is my less than right here. That's the symbol that was in my alternate. Leave that, leave that, leave that. Oh, no, I don't leave that. That is a 5. So I guess that is fine. Leave that. I named it sleep. I'm going to reset this. Or if you don't rename it sleep, that's fine. This was a 30. Looks like I have some old stuff in here that I did. 0.292 for my probability of success there. And then this was 1936, right? Calculate, and it pops up down there. I feel like I might have hit a wrong button on the amount. 11926 less 30. Where's my typo? Oh, there it is. See how it screwed up my p-value? Because that was supposed to be a 0.008, right? When I reset it, I missed it. Now it's what we want. Right? But see how the test stat didn't change. It's gathering up how much extra there is. That will change. Whoop. I think I got one more on this one. 57 out of 104 pregnant women correctly guessed the sex of their babies. So we want to test the claim that the success rate is the same as just guessing. Like you got a 50-50 chance of guessing. So I'm going to say that it's the same as just guessing. My claim is that it's just the same as guessing, that it's equal to 0.5. That's my claim. Well, what's the opposite of equal to? Not equal to. And so now this is my alternate, but that's not my claim. This is my claim. So now when I go through everything that I'm going to go through, I'm going to take kind of the same steps, but now my dartboard looks like this, right? I have some on each side. I can find it using the calculator. I can find it using Statlet. I can find it however I want to find it, but I'm probably just going to skip right down to the test and make this an equal to. Leave this to 0.05. That's the most common. This still says sleep. Don't worry about that. 50% in there. But my sample data was 57 out of the 104 women said that they got it right, guessed right. So a little bit more than half. And I hit calculate test. Ooh, p-value is big. Is 0.3268 less than 0.05? No. It's way too big. If the p is low, the null goes. That means if the p is not low, the null ain't going anywhere. So I'm going to fail to reject the null this time. So when I look at my these pieces here, I get to keep this and I throw that one out. But that makes me happy because that was the one that was starred. So I get to say, like, I'm right. Doesn't sound like I'm right though, right? Did your original claim contain the equality? Yes, actually this time. Did you reject the null? No. There's not sufficient evidence to warrant the rejection of the claim. So I can't say I'm right. But that's basically saying you can't tell me I'm wrong yet. You have to keep doing more. So that's why I like to star it. So I know, like, is there a glimmer of hope for me here? Like, should I do more studies or am I done? Oh, I didn't want to do any more of the. the lab one. I thought I deleted that. So I'm going to back out of that. You can do this on your calculator. If you want to do a one prop z-test on here, you go into stat. I had to remember. You stat over to test, and then it's right here, one prop z-test instead of int. And so let's do the baby question. That is what is in your null and your alternate. This was the number of people who guessed their baby's sex correct out of all of the people. And then this was what I wanted. Now, if I wanted something else, I would move it over and hit enter. But that's what I want. I would probably say use draw, because calculate's going to give you a bunch of stuff that you don't need. And if you can see that on the screen, that's a bad sign. That's usually a fail to reject the null. And that, see how it gives you your test stat and your p-value on here? But it doesn't give you like the critical value, so you'd have to just only use the p-value. The good news is doing something for the mean is basically the same exact thing. You got X bar, we got S. Don't worry so much about the population mean. We don't really use that. We'll just go ahead and say U, and it's still sample size. Technically, same conditions have to be met as you did with your confidence intervals for a mean. Simple random sample. It's either got to be normally distributed or greater than a 30 for an N. This is the terrible looking test stat. Again, you can do all of this by hand, but you won't. Right? You can look up different critical values and all that DF values by hand or with StatLib, but whoop, I scrolled, but we usually don't do that. The requirement reason is the same as it was for the confidence intervals. As it gets bigger and bigger, it gets closer and closer to what's going on with the actual z-score table, so we don't have to worry as much. Let's jump to a study. Here we go. More sleep. So let's say author obtained a time of sleep for randomly selected adult subjects, and we found that this data down here was how many hours they slept in a night. So I have 12 numbers, and I could find the mean and the standard deviation this way. You can sometimes do it inside of a calculator, depending that the calculator they use, but I have found that the Stats Kingdom one is not great for that. So common recommendation is that adults should sleep between 7 and 9 hours a night. We're going to use a p-value method because that's the easiest one for us to test the claim with a 0.05 significance level that the amount of sleep that adults are sleeping is less than 7 hours. So I'm saying that the mean amount of sleep that people are getting is less than 7 hours. That's my claim. What's the opposite of less than? Greater than or equal to. So that means if I say equal to, greater than or equal to, that's my null. So this is going to be my H sub 0, and this is my H sub 1. In the real world, you would check it, and you can check the normality by making graphs and different kinds of things like that, but we won't worry about that. So here is my null, here's my alternate, and this is my claim. So I'm holding these two things. I'm hoping that I say reject the null, so I have to throw that away, and I'm left holding the less than 7. So it's a 0.05 significance level and a less than. So I got a left tail test. Oop, like this. Now, this is a real pain because I'm in t-score world, and I don't know what that is. So I'd have to look all of that stuff up to see what this critical t value is. But I can find the test stat relatively simple by hand if I wanted to, and that would be a negative 0.290. So the question is, does negative 0.290 land on this side or on this side? Now that's pretty low, so I'm going to guess it's in the big zone. You can do it on your calculator. You can run a t-test. We have the stats this time, so you would put in all these values. This is the number from your statements. That's your mean, that's your standard deviation, that's n. match it, and then of course that's calculate, and you can see we got a critical T and a very big p-value. So we know 0.3887, not less than 0.05, so I'm going to fail to reject the null. Fail to reject the null, which is bad because I had my, where's my null? That means I have to keep this, which means this goes in the garbage. So if I go to my chart, that means I'm all the way down at, did my original claim contain the equality? No. Did I reject the null? No. There's not sufficient sample evidence to support my claim. So I said they were sleeping less than 7 hours, but they're really not. I could go to a chart or a p-value or a statlet or something like that and look up what that cutoff value is. That's kind of a pain. Not when I can go to my one sample t-test calculator, which is good when you plug in the actual values, which I'm going to give you that if I can find it on here. There we go, one sample t-test coming in. Now you may remember that it gave us the value, the data. I found that it doesn't work well when you put in the data. It gets confused. So I went here and I would calculate the mean and the standard deviation and then type it in. You could also use this other one if you wanted to for the mean. Either one is fine. Either one, though, is going to require you finding out what the mean and the standard deviation is if they give you a list of numbers like wherever it is. This. It's just not as friendly as the confidence interval ones. I don't know why. But you match up these values just like you did before. You put in your significance value, and then you pretty much leave, oh, here's the number that is in your hypotheses. And that I kind of just leave everything else alone here, right? Just fill in those first three. And then there's like a little bit of a gap. You can see that you have a choice here between putting in the data or putting in the actual like X bar and standard deviation. That's what you want to do. It just doesn't work great with the data. You can name the group or not, put in your sample average, your sample standard deviation, and your N. When you hit calculate, it's going to spit it out to you. And that's it. You get your test stat, you get your p-value, and of course, you know, hiding in there is going to be that critical value. We have just a couple of minutes for, I think, the one or two more. I'll show you how the calculator, when I'll pull up the calculator one. Maybe let's skip to this one. Statistics students believe that the mean score in the first stats test is a 65. The stats instructor thinks the mean score is higher than 65. He samples 10 stat students and finds their scores to be this. And he performs a hypothesis testing using a 0.05%, right? So that 0.05, excuse me, because that's what 5% is as a significance level, to test this claim. Well, my claim is that the mean is higher than 65. That's my claim. The opposite of greater than is less than or equal to, and if I say equal to, I have the null. So there we go. Those are my two hypothesis statements. Right. There's my claim. Here's my significance level. So if I was going to draw this map, this is going to be a right tail test. It's all right up here. And all that error is going to go in there. And I'm going to throw a dart at the map. And if I land in this zone, then that's going to be a fail to reject. And then if I land in this zone, that is a reject. But I don't know where this is. It's a t-score. It's a big pain to look up. So what I'm going to do is I'm going to find my test stat so I don't have to do this and figure out what that critical value is. But I'm not going to do that by hand. There's no need, right? I have my calculator. So let's pull up the calculator and type this fun stuff in. So many tabs. Okay. So my alternate was a greater than. So I'm going to put that in like that. Make this bigger so you can see it. My significance level is a 0.05. I'll leave that. My expected mean. So this is the thing that is inside of the hypothesis statement, 65. I'm going to leave everything else alone up here. Now, it gave me data. It does not, like you can click that. It's not cooperating because this does a little bit more than we really need it to do. So I'm going to leave it like this, and I'm going to go over to my descriptive statistics calculator, and I'm going to grab my data values. Whoops. And go like this and pop them in there. And that is a sample calculate. And my mean is a 67. My standard deviation, let's go 3197. I'm going to come back to this. Scroll down some more past the spam and say 67. I had 3.197 and n is 10. Like that. Go ahead, calculate. And this is what I'm interested in. P-value, that's what I'm most interested in because I'm going to use a p-value method. It does give me this critical value right here. Wow, that's pretty serious. That does not land in there. 1.97 is not a part of the acceptance region. So it's pretty, oh, there it is. Here we go. It's right here. 1.833. So this lands past that. So it's higher. If that's a pain, and it is a little bit of a pain, then use your p-value. Is that less than 0.05? Yes. So that means I'm going to reject the null. All right, I got all that stuff in there. You could also use this other calculator to get kind of a different version of the same thing. Did my original claim contain the equality? No, I said it was greater than. Did I reject the null? Yes. So that's great news. If I come back here and I can only keep one and I have to reject the null, that means this goes in the garbage, which means I get to keep that, which is good news. As good news as stats can be, the sample data supports my claim. Can't say I'm 100% right, but I can say I can support the claim. Look, it's looking good, like I was on the right track. So those are your two hypothesis tests for this week. Population proportion and mean. I am going to turn off the recording and find out what questions you have.